Hello there, and welcome to the Sleepy Scientist's channel. I'm so glad you found your way here tonight. Maybe you've had a long day filled with thoughts that won't settle, or perhaps you're simply the kind of person who finds comfort in the vastness of the universe, in ideas so large they make everything else feel small and manageable. Either way, you're in exactly the right place. You have nothing to do right now but rest. Let your muscles relax, your breathing slow, and your mind drift into the gentle current of curiosity. Because tonight, we're exploring one of the most mysterious, most powerful, and most misunderstood phenomena in all of existence: black holes. These aren't the destructive monsters of science fiction, though they are powerful beyond measure. They're not cosmic vacuum cleaners, though their gravity is immense. They are quite simply places where the universe has folded in on itself, where the fabric of space and time has been pulled so taut that reality itself changes shape. Over the next hour or so, we'll drift through the science, the mystery, and the quiet wonder of these cosmic enigmas. We'll talk about how they form, what they do to space and time, and the strange radiation that allows them to slowly evaporate into nothingness over timescales longer than you can imagine. You'll hear about the first photographs ever taken of a black hole's shadow, the gravitational waves that ripple through the universe when two black holes collide, and the supermassive giants that lurk at the hearts of galaxies, including our own. Some of what you hear might surprise you. Much of it might spark your curiosity, but all of it is meant to carry you gently towards sleep, one cosmic fact at a time. And before we begin, if these calm explorations of the universe help you unwind at the end of your day, or if you simply want to support more content like this, please consider liking this video and subscribing to the channel. It helps others find their way here, one sleepy soul at a time. Let's begin. The nature of black holes. A black hole is not really a hole at all. It's a region of space where matter has been compressed so densely and gravity has become so intense that the very structure of space-time warps beyond recognition. The name itself is a bit misleading, though evocative. These objects don't lead anywhere, don't open into other dimensions or universes. They are simply places where gravity has won completely. At the heart of every black hole lies something called a singularity. This is a point of infinite density, where all the mass of the black hole is compressed into a space with zero volume. The mathematics breaks down here. The laws of physics as we understand them cease to function. We don't know what actually exists at the center of a black hole, because our equations, brilliant as they are, cannot describe conditions of infinite density and infinite curvature. It's one of the great mysteries of physics, a place where general relativity meets its limit and quantum mechanics should take over. Except we don't yet have a theory that successfully combines the two. Surrounding the singularity is the event horizon. This is the boundary beyond which nothing can escape, not even light itself. The event horizon is not a physical surface like the surface of Earth or the Sun. You could pass through it without feeling anything particular at that moment. There's no wall, no barrier, no membrane. It's simply a mathematical boundary in space, a point of no return defined by gravity alone. The size of the event horizon depends on the mass of the black hole. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. That means if you could compress the entire mass of the Sun into a sphere just 6 kilometers across, it would become a black hole. For more massive black holes, the event horizon is larger. The supermassive black hole at the center of our galaxy has an event horizon about 17 times larger than the Sun itself. even though it contains the mass of over 4 million suns. Once something crosses the event horizon, it is lost to the outside universe forever. All information about what fell in, all the particles, all the energy, appears to be trapped. This creates one of the most profound puzzles in modern physics, the black hole information paradox, which we'll explore later in this journey. The name black hole wasn't coined until 1967, when physicist John Wheeler used the term in a lecture. Before that, these objects were called frozen stars or collapsed stars. And for decades, many physicists weren't even sure they could exist in nature. They were mathematical curiosities, solutions to Einstein's equations that seemed too extreme to be real. But the universe, as it turns out, is more extreme than our imaginations. Black holes are invisible by their very nature. They don't emit light, they don't reflect light, and they don't scatter light. They absorb everything that comes near them. So how do we know they're there? We observe their effects on nearby matter. When gas and dust fall toward a black hole, they heat up to millions of degrees, emitting X-rays and other radiation before they cross the event horizon. We can detect these bright accretion disks. We can also watch stars orbit around points in space that appear to contain nothing visible, their movements revealing the presence of something massive and dark. In recent years, gravitational waves have given us another way to detect black holes. When two black holes spiral into each other and merge, they send ripples through the fabric of space-time itself. These ripples, traveling at the speed of light, eventually reach Earth, where detectors like LIGO can measure them. The waves are unimaginably faint by the time they arrive, distorting space by less than the width of a proton across a distance of several kilometers. Yet we can measure them, and from those measurements we can learn about the masses, spins, and distances of the black holes that created them. Black holes come in different sizes, from stellar mass black holes just a few times heavier than the Sun, to supermassive monsters billions of times more massive. They form through different processes. They exist in different environments, but they all share the same fundamental nature. They are places where gravity has compressed matter so thoroughly that escape velocity exceeds the speed of light, and the normal rules of space and time no longer apply in the ways we're accustomed to. These objects challenge everything we thought we knew about the universe. They forced Einstein to confront the limits of his own theories. They inspired Hawking to unite quantum mechanics with gravity. They've become laboratories for testing physics in conditions we could never recreate on Earth. And yet, for all their strangeness, black holes follow rules. They obey laws. They can be studied, understood, and even predicted with remarkable precision. The universe is full of them. Astronomers estimate that our galaxy alone contains hundreds of millions of stellar mass black holes, silent and dark, most of them drifting through space undetected. Every large galaxy appears to have a supermassive black hole at its center. They are not rare cosmic accidents. They are woven into the structure of the universe itself, playing crucial roles in how galaxies form and evolve. And as we'll discover tonight, they are far stranger than their name suggests. Types and sizes. Black holes exist across an enormous range of masses. The smallest black holes that could form from the collapse of a star must be at least about 2.5 times the mass of the Sun. This minimum mass is set by physics. When a star dies, its core collapses. If the core is massive enough, not even the quantum pressure of neutrons packed together can resist gravity's pull. The core continues to collapse beyond the density of a neutron star, and a black hole forms. But if the core is below this critical mass, it stops collapsing and becomes a neutron star instead. Incredibly dense, but not quite dense enough to disappear behind an event horizon. These stellar mass black holes typically range from about 5 to several tens of times the mass of the Sun. The exact upper limit is still debated, but most stellar black holes discovered so far are in this range. They form from the deaths of massive stars, stars that were born with at least 20 times the mass of our Sun. When such stars exhaust their nuclear fuel, they explode as supernovae, and what remains of the core collapses into a black hole. Then there are supermassive black holes. These are the giants, the colossal monsters that live at the centers of galaxies. They range from hundreds of thousands to billions of times the mass of the Sun. Our own Milky Way harbors a supermassive black hole called Sagittarius A, or Sagittarius A star, with a mass of about 4 million suns. It sits quietly at the galactic center, about 26,000 light-years from Earth, pulling stars into tight, fast orbits around it. The most massive black hole ever discovered weighs in at around 40 billion times the mass of the Sun. It resides in a distant galaxy, and its event horizon is so large that it could swallow our entire solar system several times over. These supermassive black holes are so large that if you were falling toward one, you might not even notice when you crossed the event horizon. The tidal forces, the difference in gravitational pull between your head and your feet, would be relatively gentle compared to a smaller black hole. The formation of supermassive black holes remains one of the great unsolved problems in astrophysics. We don't fully understand how they grew so large. One possibility is that they formed from the direct collapse of enormous clouds of gas in the early universe. Another is that they started as smaller black holes and grew over billions of years by consuming gas, dust, and stars, and by merging with other black holes. Observations suggest that supermassive black holes were already in place when the universe was quite young, less than 1 billion years old, which makes their growth even more mysterious. Between stellar mass and supermassive black holes lies a middle category that astronomers have only recently begun to confirm. Intermediate mass black holes have masses between about 100 and 100,000 times that of the Sun. For years, these were hypothetical. Astronomers suspected they should exist, bridging the gap between the two other categories. But direct evidence was scarce. That changed with gravitational wave detections. LIGO and Virgo have observed several black hole mergers that produced intermediate mass black holes. One particularly significant detection, called GW190521, resulted from the merger of two black holes with masses of about 85 and 66 solar masses. The resulting black hole had a mass of about 142 solar masses, firmly in the intermediate range. These detections have opened a new window into understanding how black holes grow and evolve. There's also a theoretical fourth category, primordial black holes. These would be black holes that formed in the very early universe, shortly after the Big Bang, from density fluctuations in the fabric of space itself rather than from collapsing stars. Primordial black holes could have a huge range of masses, from tiny, almost subatomic, to thousands of times the mass of the Sun. The smallest primordial black holes would have evaporated long ago due to Hawking radiation, a quantum process we'll discuss in detail later. But larger primordial black holes, if they exist, could still be out there, hiding in the cosmos. Some scientists have even suggested that primordial black holes might account for some or all of the mysterious dark matter that makes up most of the mass in the universe. So far, however, searches for primordial black holes have turned up no definitive evidence. The size of a black hole's event horizon depends directly on its mass. The relationship is straightforward. If you double the mass, you double the radius of the event horizon. This radius is called the Schwarzschild radius, named after Karl Schwarzschild, the physicist who first derived the exact solution to Einstein's equations describing a non-rotating black hole. For a black hole with one solar mass, the Schwarzschild radius is just under 3 kilometers. For a supermassive black hole with 1 billion solar masses, the Schwarzschild radius is about 3 billion kilometers, or roughly the distance from the Sun to Neptune. These supermassive black holes are vast, but remember, all that mass is still compressed into a region of space far smaller than you might expect. The average density inside the event horizon of a supermassive black hole can actually be quite low, less than the density of air in some cases, because the volume inside the horizon grows faster than the mass as you add more material. But density isn't really the right way to think about black holes. What matters is the curvature of space-time, the intensity of the gravitational field. And at the event horizon, that curvature becomes so extreme that the paths of light itself bend completely inward, trapping everything inside. The mass of a black hole determines much more than just its size. It also determines its temperature, its rate of evaporation through Hawking radiation, and how it interacts with matter and light nearby. A small black hole is hotter and evaporates faster than a large one. A supermassive black hole is incredibly cold, with a temperature far below the ambient temperature of space, and it would take an unimaginably long time to evaporate, far longer than the current age of the universe. Black holes can also spin. In fact, most black holes probably do spin, because they form from the collapse of rotating matter. The spin affects the structure of space-time around the black hole, creating a region called the ergosphere, where space itself is dragged around in the direction of the spin. This phenomenon is called frame dragging, and it has profound implications for matter and light near the black hole. A spinning black hole can have 2 different event horizons, an outer and an inner one, depending on how fast it's rotating. The faster the spin, the smaller the outer horizon becomes. There's a theoretical maximum spin rate set by the laws of physics, beyond which the black hole would become something else entirely, perhaps a naked singularity with no event horizon at all. But such objects, if they can exist, have never been observed. In practice, black holes probably can't spin faster than a certain limit because the process of accreting matter tends to slow them down, while the emission of gravitational waves during mergers can carry away angular momentum. Still, some black holes spin extraordinarily fast, approaching the theoretical maximum. The diversity of black holes in size, mass, spin, and origin reflects the diversity of the processes that create them and the environments they inhabit. From the explosive deaths of massive stars to the quiet accumulation of matter over cosmic time, from the dense cores of globular clusters to the centers of the largest galaxies, black holes emerge wherever gravity has the opportunity to compress matter past the point of no return. And once they form, they are, in a sense, eternal. Or at least they would be, if not for a strange quantum effect discovered by Stephen Hawking. Formation and birth, the most common way a black hole forms is through the death of a massive star. Stars are engines of fusion, converting hydrogen into helium and then, in more massive stars, fusing heavier and heavier elements. This process releases energy, producing the light and heat that make stars shine. But it also creates an outward pressure that balances the inward pull of gravity. For most of a star's life, these 2 forces are in equilibrium. But fusion cannot continue forever. Eventually, even the most massive star runs out of fuel. When a star exhausts the hydrogen in its core, it begins fusing helium. When the helium is gone, it fuses carbon, then oxygen, neon, magnesium, silicon, and finally iron. But iron is special. Fusing iron doesn't release energy, it consumes energy. So when a star's core turns to iron, fusion stops. Without the outward pressure from fusion, gravity takes over. The core collapses, and it collapses fast. In less than a second, the core of a star that was once millions of kilometers across compresses to a sphere just tens of kilometers wide. The collapse is catastrophic. The outer layers of the star, no longer supported, fall inward and then rebound off the collapsing core in a shockwave that tears the star apart. This is a supernova, one of the most violent events in the universe. The explosion is so energetic that for a brief time, a single dying star can outshine an entire galaxy. The shockwave carries with it newly formed heavy elements, carbon, oxygen, iron, gold, uranium, scattering them into space, where they will eventually become part of new stars, planets, and even living beings. We are, quite literally, made of star stuff, forged in the nuclear furnaces of ancient suns and dispersed by their dying explosions. But the story doesn't end with the supernova. What happens to the core depends on how massive it is after the explosion. If the remaining core is between about 1.5 and 2.5 solar masses, it becomes a neutron star, an object so dense that protons and electrons are crushed together to form neutrons. A neutron star is essentially a giant atomic nucleus, about 20 kilometers across but containing more mass than the Sun. If the core is more massive than about 2.5 solar masses, not even the quantum pressure of neutrons can resist gravity. The core continues to collapse. It shrinks past the density of a neutron star, past any density we can comprehend, and it keeps shrinking until it disappears behind an event horizon. A black hole is born. The exact threshold between neutron stars and black holes is still uncertain, because the behavior of matter at such extreme densities is not fully understood. Observations suggest the boundary is somewhere between 2 and 3 solar masses, but the precise value depends on the properties of nuclear matter under conditions we cannot recreate in laboratories. Not all stellar black holes form from supernovae. Some massive stars, particularly the very largest ones, may collapse directly into black holes without producing a visible explosion. In these cases, the star simply dims and vanishes, its outer layers falling directly into the black hole rather than being blown away. Astronomers have observed a few candidate events that might represent such failed supernovae, but the phenomenon is still not well understood. The process of collapse is strange from the perspective of an outside observer. As the core shrinks toward the Schwarzschild radius, time dilation becomes extreme. Clocks near the collapsing matter tick more and more slowly compared to clocks far away. Light emitted from the surface becomes increasingly redshifted, its wavelength stretched by the intense gravitational field. To a distant observer, the collapse appears to slow down, the surface approaching but never quite reaching the event horizon, frozen in time. Of course, this is an illusion created by the warping of space-time. From the perspective of someone falling with the collapsing matter, there is no slowing down. The collapse proceeds in a finite amount of time, and the event horizon forms. But the light carrying that information takes longer and longer to escape, and eventually it cannot escape at all. The formation of the black hole is hidden from the outside universe. Supermassive black holes, those giants at the centers of galaxies, probably did not form from single stars. They are too massive, and they appeared too early in the history of the universe for stellar evolution alone to explain them. Several theories attempt to account for their formation, but none is completely satisfactory. One possibility is that supermassive black holes formed from the direct collapse of enormous clouds of gas in the early universe. If conditions were right, a cloud of primordial hydrogen and helium could have collapsed directly into a black hole with a mass of thousands or even hundreds of thousands of suns, bypassing the stage of star formation entirely. These intermediate mass seed black holes could then have grown over billions of years by accreting matter and merging with other black holes. Another possibility is that supermassive black holes grew from smaller seeds, perhaps stellar mass black holes or intermediate mass black holes that formed in dense star clusters. In the chaotic environment of the early universe, these seeds could have fed on gas and merged with each other, growing exponentially over time. Recent observations have found quasars, incredibly luminous objects powered by supermassive black holes in the universe when it was less than 1 billion years old. This presents a challenge. How did black holes grow so large so quickly? The rate at which a black hole can consume matter is limited by physics. When matter falls toward a black hole, it heats up and emits radiation. This radiation exerts an outward pressure that can push away more material, preventing it from falling in. This is called the Eddington limit, and it sets a maximum growth rate for black holes. For supermassive black holes to reach their observed masses in the time available, they would have to have grown at or near the Eddington limit for much of the universe's early history, or they started from much larger seeds than we typically assume. Resolving this puzzle is an active area of research, and upcoming telescopes may provide crucial clues. Intermediate mass black holes might form through several different channels. They could be the result of collisions between massive stars in dense stellar environments, like the cores of globular clusters. They could form from the direct collapse of very massive stars, hundreds of times the mass of the Sun, if such stars existed in the early universe. Or they could grow from stellar mass black holes that merge repeatedly, building up mass over time. Primordial black holes, if they exist, would have formed through entirely different mechanisms. In the first fraction of a second after the Big Bang, the universe was an incredibly hot, dense soup of energy and particles. Tiny fluctuations in density, quantum ripples blown up to macroscopic scales by the rapid expansion of space, could have created regions dense enough to collapse into black holes. These primordial black holes could span an enormous range of masses, depending on when they formed and how large the fluctuations were. The smallest ones, with masses comparable to asteroids or even smaller, would have evaporated long ago due to Hawking radiation. Larger ones could still exist, scattered throughout the universe, nearly impossible to detect, unless they happen to pass close to something we can observe. The diversity of black hole formation mechanisms reflects the richness of cosmic history. From the fiery deaths of massive stars to the turbulent conditions of the early universe, from the dense cores of star clusters to the quiet growth of galactic centers, black holes emerge from some of the most extreme events and environments the cosmos has to offer. Once formed, a black hole is remarkably simple. It is defined by just 3 properties: mass, spin, and electric charge. Everything else about the matter that fell in, its composition, its history, its structure, is erased. This is the no-hair theorem, which states that black holes have no distinguishing features or hair beyond these 3 quantities. From the outside, all black holes with the same mass, spin, and charge are identical, no matter how they formed. This simplicity is both elegant and troubling. It suggests that black holes destroy information, erasing the detailed quantum states of the matter that falls into them. And that creates a paradox, one that has haunted physicists for decades. The physics of extreme gravity, as Einstein showed, is not a force in the traditional sense. It is the curvature of space-time. Mass and energy bend the fabric of space and time around them, and objects moving through this curved space-time follow paths that we perceive as being influenced by gravity. Near a black hole, this curvature becomes extreme. Imagine space-time as a stretched rubber sheet. Place a heavy ball in the center, and it creates a dip. A marble rolling nearby will curve toward the ball, following the slope of the dip. Now imagine placing a ball so heavy that it tears through the sheet entirely. That's something like a black hole. The curvature becomes infinite at the singularity, and space-time itself folds back on itself. One of the most profound consequences of this curvature is time dilation. Time does not pass at the same rate everywhere in the universe. Clocks tick more slowly in stronger gravitational fields. Near a black hole, this effect becomes dramatic. If you were to observe someone falling toward a black hole from a safe distance, you would see them slow down as they approach the event horizon. Their movements would become sluggish. Their clock would tick more and more slowly compared to yours, and they would appear to freeze just at the horizon. Light coming from them would be redshifted, stretched to longer and longer wavelengths, until it faded from view. You would never actually see them cross the event horizon. But from the perspective of the person falling, nothing special happens at the event horizon itself. They cross it in a finite amount of time, experiencing no barrier, no wall. Time, for them, continues to pass normally. The discrepancy is a consequence of the warping of space-time. Events that take a finite time for the falling person take an infinite time as measured by a distant observer. This time dilation has measurable effects even far from black holes. Clocks on Earth tick slightly more slowly than clocks in orbit, because Earth's gravity, though weak compared to a black hole, still curves space-time. GPS satellites must account for this effect. Their clocks run faster than clocks on the ground, and if this weren't corrected, GPS coordinates would drift by several kilometers per day. Near a black hole, the tidal forces become immense. Tidal forces are differences in gravitational pull across an object. If you're standing on Earth, your feet are slightly closer to Earth's center than your head, so they feel a slightly stronger pull. The difference is tiny, imperceptible. But near a black hole, the difference can be enormous. This leads to a phenomenon often called spaghettification. If you were falling feet first toward a stellar mass black hole, the gravitational pull on your feet would be much stronger than the pull on your head. This difference would stretch you vertically while compressing you horizontally. As you got closer, the stretching would intensify. Long before you reached the event horizon, tidal forces would tear you apart at the molecular level, stretching you into a long, thin strand of atoms. The severity of spaghettification depends on the size of the black hole. For a small, stellar mass black hole, the tidal forces at the event horizon are extreme. You would be torn apart well before crossing, but for a supermassive black hole, the event horizon is so far from the singularity that the tidal forces at the horizon are relatively gentle. You could, in theory, cross the event horizon of a supermassive black hole without immediately being destroyed. Of course, once inside, your fate would be sealed. You would inevitably fall toward the singularity, and as you did, the tidal forces would grow stronger, eventually destroying you. Light itself behaves strangely near a black hole. In normal space, light travels in straight lines, but in curved space-time, light follows curved paths. Near a black hole, the curvature is so extreme that light can be bent into circular orbits. There's a distance from the black hole, about 1.5 times the Schwarzschild radius, called the photon sphere. At this distance, light can orbit the black hole in a circle. These orbits are unstable. Any slight perturbation, and the light either falls into the black hole or escapes to infinity. But if you could somehow position yourself at the photon sphere and look around, you would see the back of your own head. Light from you would orbit the black hole and return to your eyes. Closer to the event horizon, the bending of light becomes even more extreme. No matter which direction you point, much of the sky would be filled with distorted images of distant stars and galaxies, their light bent around the black hole by its gravity. This is gravitational lensing, and it's one of the ways astronomers detect black holes. When a black hole passes between us and a background star, the star's light is bent and magnified, creating a characteristic pattern. At the event horizon itself, space-time is so curved that all future paths lead inward. The very concept of outward ceases to exist. Inside the event horizon, the singularity is not a place in space. It is a moment in time. No matter what you do, no matter which direction you try to move, you will reach the singularity in your future. It's as inevitable as tomorrow. For a rotating black hole, the situation is even stranger. The rotation drags space-time around with it, a phenomenon called frame dragging. Outside the event horizon, there's a region called the ergosphere, where space-time is dragged so strongly that nothing can remain stationary. Even light would be pulled around in the direction of the black hole's spin, but within the ergosphere, it's still possible to escape. The event horizon lies deeper, inside the ergosphere. This rotation creates opportunities for extracting energy from a black hole. In theory, if you dropped an object into the ergosphere and split it in the right way, one piece falling into the event horizon and the other escaping, the escaping piece could have more energy than the original object. This is called the Penrose process, and it could power some of the most energetic phenomena in the universe, like the relativistic jets that blast from the poles of some black holes. The spinning black hole also has a strange property. It can have more than one event horizon. There's an outer horizon and an inner horizon, and between them lies a region of space-time with bizarre properties. Crossing the inner horizon would lead not to a singularity, but to a region where the geometry of space-time becomes wild and unpredictable, filled with infinitely blue-shifted light and other exotic effects. Whether such a region could actually exist in a real black hole, or whether quantum effects would smooth it out, remains an open question. At the heart of all these phenomena is the extreme curvature of space-time. Near a black hole, the rules we take for granted break down. Time and space exchange roles. Directions become meaningless. The future becomes inescapable. And yet, through careful mathematics and observation, we can still make predictions. Still understand, however imperfectly, and what happens in these extreme environments. Black holes are nature's ultimate laboratories for testing general relativity. They take Einstein's equations to their limits, revealing consequences that even he found difficult to accept. And in studying them, we learn not just about black holes, but about the fundamental nature of space, time, and gravity itself. Hawking radiation and thermodynamics. For decades after their theoretical prediction, black holes were thought to be perfect, eternal prisons. Nothing could escape them. They could only grow, never shrink. But in 1974, Stephen Hawking made a discovery that changed everything. He found that black holes are not entirely black. They emit radiation. This discovery was shocking. It suggested that black holes have a temperature, that they glow with thermal radiation, and that they can, over unimaginable spans of time, evaporate completely. Hawking radiation arises from quantum effects near the event horizon. In quantum field theory, what we think of as empty space is not truly empty. It's filled with quantum fluctuations, pairs of particles and antiparticles that spontaneously appear and then annihilate each other almost instantly. These are called virtual particles, and they exist for such a short time that they don't violate the conservation of energy thanks to the uncertainty principle. Near the event horizon of a black hole, something strange happens to these virtual pairs. If a particle-antiparticle pair appears just outside the horizon, one member of the pair can fall into the black hole before they have a chance to annihilate. The other particle, now lacking its partner, becomes a real particle and escapes to infinity. To a distant observer, it looks like the black hole has emitted a particle. But where does the energy for this real particle come from? It comes from the black hole itself. The particle that fell in had negative energy, as measured by an observer at infinity, and this negative energy reduces the mass of the black hole. Slowly, over time, the black hole radiates away its mass, one particle at a time. The temperature of this radiation is inversely proportional to the mass of the black hole. Small black holes are hot. Large black holes are cold. A black hole with the mass of the Sun would have a temperature of about 60 billionths of a degree above absolute zero. That's far colder than the cosmic microwave background radiation that fills space, which is about 2.7 degrees above absolute zero. So a solar mass black hole would actually absorb more energy from the universe than it radiates, and it would grow, not shrink. But a smaller black hole, one with the mass of a large mountain, would have a temperature comparable to room temperature, and an even smaller black hole, with the mass of a small asteroid, would glow white hot. These tiny black holes, if they exist, would emit a torrent of radiation, including high-energy gamma rays. The rate of evaporation increases as the black hole shrinks. A smaller black hole is hotter, so it radiates faster, which makes it shrink faster, which makes it hotter still. The process accelerates in a runaway feedback loop. In the final moments of its life, a small black hole would explode in a burst of energy, releasing the remainder of its mass in a fraction of a second. For a solar mass black hole, the time it would take to evaporate through Hawking radiation is about 10 to the 67th power years. That's 10 followed by 67 zeros, a number so large it's almost meaningless. The current age of the universe is only about 14 billion years, or about 10 to the 10th power years. So even the smallest stellar mass black holes will outlast the stars by an unimaginable margin. Supermassive black holes would take even longer to evaporate, time scales measured in 10 to the 100 power years or more. By the time they finally disappear, the universe will be a cold, dark, empty place, with all stars long since burned out, all matter decayed or frozen, and only the faintest whispers of radiation drifting through infinite space. But primordial black holes, if they formed with small masses in the early universe, could be evaporating right now. A primordial black hole with an initial mass of about 1 billion kilograms would just be finishing its evaporation today, after roughly 14 billion years. Astronomers have searched for the gamma ray bursts that would signal the final explosion of such a black hole, but so far none have been definitively observed. Hawking radiation has profound implications for the nature of black holes. It means they have thermodynamic properties, temperature, entropy, and a finite lifespan. The entropy of a black hole, a measure of its disorder or the amount of information it contains, is proportional to the area of its event horizon, not its volume. This is strange. For ordinary objects, entropy is proportional to volume, but for black holes, it's the surface area that matters. This relationship suggests something deep about the nature of information and gravity. It hints that the information about what's inside a black hole might somehow be encoded on its surface, like a hologram. This idea has led to the holographic principle, a concept in theoretical physics that proposes that the entire universe might be described by information encoded on a distant boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. But Hawking radiation also creates a paradox. If a black hole evaporates completely, what happens to the information about the matter that fell in? Quantum mechanics says that information cannot be destroyed. It can be scrambled, hidden, transformed, but not lost. Yet, if a black hole evaporates into random thermal radiation, it seems like the information about the initial state of the infalling matter is gone forever. This is the black hole information paradox. It has troubled physicists for nearly 50 years. Many solutions have been proposed. Perhaps the information is subtly encoded in the Hawking radiation, hidden in correlations too delicate to detect. Perhaps the black hole doesn't evaporate completely, but leaves behind a remnant, a tiny, stable object that contains the information. Perhaps information can be lost, and quantum mechanics needs to be revised. Or perhaps the entire framework of semi-classical gravity, which treats space-time classically while treating matter quantum mechanically, breaks down near black holes. Recent theoretical work, particularly in the realm of quantum gravity and string theory, suggests that information is not lost. Calculations involving the Page curve, a measure of how information escapes from a black hole over time, indicate that information does eventually leak out in the Hawking radiation, but only after about half the black hole's mass has evaporated. The mechanism by which this happens is still not fully understood, but it seems to involve subtle quantum effects that connect the interior and exterior of the black hole in ways that semi-classical calculations miss. The thermodynamics of black holes also connects them to the ultimate fate of the universe. In the far future, black holes may be the last objects to persist. Once all stars have burned out and all matter has either decayed or been swallowed by black holes, the universe will enter an era dominated by these dark remnants. Slowly, over timescales that dwarf the current age of the universe, the black holes will evaporate through Hawking radiation, returning their mass to the void as faint whispers of light. And then, perhaps, there will be nothing left but a cold, dark expanse, a universe in its ultimate state of entropy, with no structure, no energy gradients, no way to do work or create order. This is sometimes called the heat death of the universe, and black hole evaporation is the final chapter in that long, slow decline. But these are times so far in the future that they strain comprehension. For now, in the universe we inhabit, black holes are growing, not shrinking. They are fed by stars and gas, and they play vital roles in the structure and evolution of galaxies. Hawking radiation, for all its theoretical importance, is a vanishingly small effect in the present cosmos. Yet it reminds us that even the most permanent-seeming objects in the universe are temporary. Black holes, for all their power and mystery, are not eternal. They have beginnings and they have ends. And in their slow, quiet evaporation, we see the triumph of quantum mechanics over gravity, the victory of information over entropy, and the enduring strangeness of the universe we live in. Gravitational waves and detection. For most of human history, we observed the universe with light. Visible light, radio waves, X-rays, gamma rays, all different forms of electromagnetic radiation. But light is not the only way the universe speaks. There is another channel, invisible and silent, but carrying information from some of the most violent events in the cosmos. Gravitational waves. These are ripples in the fabric of space-time itself, created when massive objects accelerate. Einstein predicted their existence in 1916, just a year after he published his general theory of relativity. He showed that just as accelerating electric charges create electromagnetic waves, accelerating masses create gravitational waves. But he also calculated that they would be almost impossibly faint, so weak that he doubted they could ever be detected. For decades, gravitational waves were a mathematical curiosity, a prediction of the theory, but with no practical way to observe them. Then, in the 1970s, astronomers found indirect evidence. They studied a binary pulsar, two neutron stars orbiting each other, and measured how the orbit was changing over time. The stars were gradually spiraling closer together, exactly as they would if they were losing energy to gravitational waves. This was compelling evidence that the waves were real, and it earned Russell Hulse and Joseph Taylor the Nobel Prize in 1993. But direct detection, actually measuring a gravitational wave passing through Earth, remained out of reach for decades. The challenge is immense. A gravitational wave from even the most violent cosmic event would distort space-time by an incredibly tiny amount. Imagine taking a stick 4 kilometers long and stretching it by less than the diameter of a proton. That's the kind of precision required. In the 1990s, construction began on the Laser Interferometer Gravitational Wave Observatory, or LIGO. LIGO consists of two identical detectors, one in Louisiana and one in Washington state, each with two arms 4 kilometers long arranged in an L shape. Powerful lasers bounce back and forth along the arms, and sensitive instruments measure the lengths with extraordinary precision. When a gravitational wave passes through, it stretches space in one direction and compresses it in the other, causing tiny changes in the arm lengths that the lasers can detect. On September 14, 2015, just days after LIGO began its first observing run with upgraded detectors, a gravitational wave passed through Earth. The signal lasted just 0.2 of a second, a brief chirp rising in frequency as two massive objects spiraled together and merged. The detectors in Louisiana and Washington both recorded it, arriving at Louisiana 7 milliseconds before Washington, consistent with a wave traveling at the speed of light from a source in the southern sky. Analysis of the signal revealed its source. It came from the merger of two black holes, one about 36 times the mass of the Sun, and the other about 29 times. They had been orbiting each other, gradually drawing closer as they lost energy to gravitational waves. And finally, they collided. In a fraction of a second, they merged into a single black hole of about 62 solar masses. 3 solar masses, the difference between the sum of the two original black holes and the final black hole, were converted directly into energy and radiated away as gravitational waves. This was more energy than all the stars in the observable universe emit as light in that same fraction of a second. And we detected it. A whisper from 1.5 billion light-years away. The discovery was announced in February 2016. and it marked the beginning of a new era in astronomy. For the first time, we could observe the universe not with light, but with gravity itself, and black holes, invisible to telescopes, were suddenly observable in a completely new way. Since that first detection, LIGO, in collaboration with the Virgo detector in Italy and the Kagra detector in Japan, has detected hundreds of gravitational wave events. Most are black hole mergers, but some are collisions between neutron stars, and others involve one black hole and one neutron star. Each detection provides a wealth of information: the masses of the objects, their spins, how their orbits were oriented, and how far away they were when the merger occurred. The signals themselves are hauntingly beautiful. Converted into sound, they produce a characteristic chirp, a rising tone that sweeps from low frequencies to high as the objects spiral faster and faster before merging. Each merger has a unique chirp, a gravitational fingerprint determined by the masses and spins of the merging objects. One particularly significant detection, called GW190521, captured the merger of two black holes with masses of about 85 and 66 solar masses. The resulting black hole had a mass of about 142 solar masses, making it the first clear detection of an intermediate mass black hole. The signal was brief, just 4 quick wiggles lasting less than 1/10 of a second, but it came from about 5 billion light years away, when the universe was about half its current age. More recently, in November 2023, LIGO and its partners detected the most massive black hole merger to date. The event, designated GW2I311223, involved black holes of about 100 and 140 solar masses, producing a final black hole of 225 solar masses. The black holes were spinning rapidly, near the limit allowed by general relativity, and the signal pushed the detectors to their limits. These detections have revealed that black holes are more common, more massive, and more diverse than previously thought. They've also confirmed predictions of general relativity with incredible precision. The gravitational waves travel at exactly the speed of light, as Einstein predicted. They carry energy away from the merging system, causing the orbits to shrink, exactly as expected. And the final ring down, the way the merged black hole settles into its final state, matches theoretical calculations. But gravitational waves carry information that light cannot. Because black holes are dark, we can only observe them through their effects on nearby matter or through their gravitational influence. Gravitational waves let us hear the black holes directly, measuring their masses and spins with precision, watching them spiral together and listening to the final moments of their separate existences. Gravitational wave astronomy also allows us to observe events that produce no light at all. Binary black hole mergers, unlike neutron star mergers, are dark events. There's no explosion, no bright flash, no afterglow, just the silent release of gravitational energy. Without gravitational wave detectors, we would never know these events were happening. In August 2017, LIGO and Virgo detected the merger of two neutron stars. Unlike black holes, neutron stars are made of matter, and when they collide, they produce a spectacular display of light. Telescopes around the world swung into action, observing the event in gamma rays, X-rays, visible light, radio waves, and more. This was the first multi-messenger observation of a gravitational wave source, combining gravitational wave data with electromagnetic observations. The neutron star merger confirmed several important predictions. It showed that at least some short gamma ray bursts, mysterious flashes of high-energy light that last only seconds, are caused by neutron star collisions. It also demonstrated that heavy elements like gold and platinum are forged in these mergers, scattered into space to eventually become part of new stars and planets. Gravitational wave astronomy is still in its infancy. The current generation of detectors is sensitive enough to detect mergers out to billions of light years, but future detectors will be even more powerful. Plans are underway for the Einstein telescope in Europe and Cosmic Explorer in the United States, detectors that could observe gravitational waves from black hole mergers anywhere in the observable universe. There are also plans for space-based detectors, like the Laser Interferometer Space Antenna, or LISA. Space-based detectors would have arms millions of kilometers long, far longer than any detector on Earth, allowing them to detect lower frequency gravitational waves from supermassive black hole mergers, waves that LIGO cannot detect because they oscillate too slowly. With these future detectors, we'll be able to observe the universe in ways we can barely imagine. We'll watch supermassive black holes collide when galaxies merge. We'll detect gravitational waves from the early universe, perhaps even from the Big Bang itself. We'll probe the interiors of neutron stars, test general relativity in the most extreme conditions, and perhaps discover new phenomena that we haven't predicted. Gravitational waves have opened a window on the universe that was closed for all of human history. And through that window we've seen black holes not as theoretical curiosities or distant mathematical objects, but as real, dynamic, colliding entities, shaping the cosmos with their immense power. Each detection is a story, a moment in the life of the universe captured in ripples of space-time, travelling across billions of light years to reach us, to shake our detectors by less than the width of an atom, and to tell us that out there, in the vast darkness, black holes are dancing. Supermassive black holes and galaxies. At the centre of nearly every large galaxy, hidden behind clouds of gas and dust, lies a supermassive black hole. These are not the remnants of dead stars. They are ancient, colossal entities, millions or billions of times more massive than the Sun, and they play a fundamental role in the evolution of their host galaxies. Our own Milky Way harbours such a giant. It's called Sagittarius A, or more commonly, Sagittarius A star, and it sits at the galactic centre, about 26,000 light-years from Earth. For decades, astronomers tracked stars orbiting this invisible point, watching them whip around in tight ellipses at speeds reaching several % of the speed of light. The orbits revealed a mass of about 4 million suns, concentrated in a region smaller than the orbit of Mercury. There was only one plausible explanation: a supermassive black hole. In 2020, this discovery earned Reinhard Genzel and Andrea Ghez the Nobel Prize in Physics. They had spent years patiently observing the motions of stars near the galactic center, mapping their orbits with increasing precision, and proving beyond doubt that a supermassive black hole exists at the heart of our galaxy. Sagittarius A star is relatively quiet. It doesn't consume much matter. It doesn't blaze with light. Occasionally it flares in X-rays as small amounts of gas fall in, but for the most part it sleeps. This is typical of many supermassive black holes in the present-day universe. They had their heyday in the distant past, during the youth of their galaxies, when gas and stars were more plentiful and collisions more frequent. Now they are quiescent, waiting. But not all supermassive black holes are quiet. Some feed voraciously, pulling in gas and dust and stars from their surroundings, heating this material to millions of degrees as it spirals inward. These actively feeding black holes are some of the brightest objects in the universe. They are called active galactic nuclei, or AGN. The brightest AGN are quasars. These are supermassive black holes surrounded by enormous accretion disks. Disks of matter spiraling inward and shining with the light of billions of suns. Quasars were more common in the early universe, when galaxies were young and gas was abundant. Today they are rare, but they still exist, shining from billions of light years away, their light carrying information about conditions in the young cosmos. In April 2019, astronomers released the first image of a black hole. The target was not Sagittarius A star, but a much more massive and distant black hole in the galaxy M87, about 55 million light-years away. This black hole has a mass of about 6.5 billion suns, over 1,000 times more massive than the one in our galaxy. The image, captured by the Event Horizon Telescope, a global network of radio telescopes working together as a single Earth-sized instrument, showed a dark shadow surrounded by a glowing ring of hot gas. The shadow is the event horizon, or more precisely, the region around the horizon where light is so strongly bent that it cannot escape. The ring is the accretion disk, glowing at millions of degrees. The image was a triumph of technology and coordination, and it confirmed predictions of general relativity with stunning precision. The size and shape of the shadow matched what Einstein's equations predicted for a black hole of that mass. The ring was brighter on one side because the black hole is spinning, and the side rotating toward us appears brighter due to the Doppler effect. In May 2022, the Event Horizon Telescope released a second image, this time of Sagittarius A star. The image showed a similar structure, a dark shadow surrounded by a glowing ring, though capturing it was much more difficult because Sagittarius A star is smaller and its surroundings change rapidly. The agreement between the observed images and theoretical predictions was, once again, remarkable. These images are not photographs in the traditional sense. They are reconstructions built from radio observations at millimeter wavelengths, the only wavelengths that can penetrate the dust and gas around the galactic center. But they are real, a direct view of the environment just outside a black hole's event horizon, and they represent one of the greatest achievements in observational astronomy. Supermassive black holes are not just passive inhabitants of galactic centers. They actively shape their galaxies. When a supermassive black hole feeds, it releases enormous amounts of energy, not just as light, but as powerful winds and jets of particles traveling at nearly the speed of light. These outflows can blow gas out of the galaxy, shutting down star formation and limiting the galaxy's growth. This feedback process appears to regulate the relationship between supermassive black holes and their host galaxies. Observations show a tight correlation between the mass of a galaxy's central black hole and the mass of its bulge, the dense central region of stars. More massive bulges host more massive black holes. The ratio is remarkably consistent across a wide range of galaxy types, suggesting that the black hole and the galaxy evolved together, each influencing the other. How this relationship is established remains an active area of research. It may be that the same processes that form the bulge also feed the black hole, or that outflows from the black hole regulate how much gas can form stars in the bulge. Or perhaps both processes matter, creating a complex feedback loop that shapes both the black hole and the galaxy. Some supermassive black holes launch relativistic jets, narrow beams of particles and magnetic fields that shoot out from the poles at nearly the speed of light. These jets can extend for millions of light years, far beyond the galaxy itself, carving out giant lobes of radio-emitting plasma in the intergalactic medium. The mechanism that produces these jets is not fully understood, but it seems to involve the black hole's spin and the magnetic fields threading through the accretion disk. One leading theory is the Blandford-Znajek process, which extracts energy from the black hole's rotation and channels it into the jets. The jets carry away enormous amounts of energy, enough to influence the evolution of entire galaxy clusters. Supermassive black holes also play a role in galaxy mergers. When two galaxies collide, their central black holes eventually sink toward the center of the merged system, orbiting each other and emitting gravitational waves. Over millions of years, the orbit decays and the black holes spiral together and merge, producing a brief but intense burst of gravitational waves. Future space-based detectors like LISA will be able to observe these mergers directly, detecting the low-frequency gravitational waves they produce. This will allow astronomers to study the growth of supermassive black holes over cosmic time, tracing their evolution from the early universe to the present day. The existence of supermassive black holes in the early universe remains a puzzle. Observations have found quasars powered by billion solar mass black holes when the universe was less than 1 billion years old. Growing a black hole to such a mass in such a short time is difficult. It requires either very efficient feeding, starting from unusually massive seeds, or mechanisms we don't yet understand. Some theories propose that supermassive black holes formed from the direct collapse of primordial gas clouds, creating intermediate mass seeds that then grew through accretion and mergers. Others suggest that dense star clusters in the early universe could have produced intermediate mass black holes through repeated collisions, providing the seeds for later growth. Whatever the mechanism, the existence of supermassive black holes in the early universe suggests that they played an important role in the formation of the first galaxies, perhaps even helping to regulate the process of galaxy formation itself. In the present universe, supermassive black holes are embedded in a complex ecosystem. They feed on gas and stars, launch winds and jets, influence star formation, and shape the evolution of their host galaxies. They are not isolated objects, but active participants in the cosmic dance, intimately connected to the galaxies they inhabit. And they wait, patient and powerful, at the centers of galaxies, ready to flare into brilliance whenever fresh material falls within their reach, shaping the universe one galaxy at a time. Accretion disks and jets. When matter falls toward a black hole, it doesn't fall straight in. It carries angular momentum, a tendency to spin, and this spin causes it to spiral inward rather than plunge directly. As it spirals, it forms a disk, a rotating, flattened structure of gas and dust called an accretion disk. Accretion disks are where much of the action happens around black holes. They are incredibly hot, incredibly bright, and incredibly dynamic. As matter in the disk spirals inward, friction between particles converts gravitational potential energy into heat. The inner regions of the disk, closest to the black hole, can reach temperatures of millions or even billions of degrees. At these temperatures, the disk emits radiation across the entire electromagnetic spectrum. The inner regions glow in X-rays. The outer regions emit visible and ultraviolet light. And throughout the disk, charged particles spiraling in magnetic fields emit radio waves. This radiation is how we detect many black holes, by the light from the matter falling into them. The structure of an accretion disk depends on how fast matter is falling in. If the inflow rate is low, the disk is thin and relatively cool, with materials spiraling inward slowly over thousands of years. This is called a thin disk, and it's what forms around many stellar mass black holes in binary systems and around relatively quiet, supermassive black holes. If the inflow rate is high, the disk becomes thick and turbulent, bloated by radiation pressure and magnetic fields. This is called a thick disk or an advection-dominated accretion flow. In such disks, the matter falls inward quickly, and much of the energy is carried into the black hole rather than being radiated away. Accretion disks are not static. They are threaded with magnetic fields, and these fields create turbulence and instability. One important process is the magneto-rotational instability, which causes the disk to become turbulent, allowing angular momentum to be transferred outward and enabling matter to spiral inward. Without this process, accretion would be much slower, and black holes would grow much more slowly. The inner edge of the accretion disk is set by the innermost stable circular orbit, or ISCO. This is the closest distance to the black hole where matter can orbit stably. Inside the ISCO, orbits are unstable and any matter there quickly plunges into the black hole. For a non-rotating black hole, the ISCO is at 3 times the Schwarzschild radius. For a maximally spinning black hole, the ISCO can be as close as half the Schwarzschild radius, allowing matter to orbit much closer before falling in. The location of the ISCO affects the disk's brightness and spectrum. When the ISCO is closer to the event horizon, the disk is hotter and emits more high-energy radiation. By studying the spectrum of light from an accretion disk, astronomers can estimate the spin of the black hole, one of its 3 fundamental properties. Some black holes launch powerful jets, narrow beams of particles and magnetic fields that shoot out from near the poles at close to the speed of light. These jets are some of the most energetic phenomena in the universe, carrying away more energy than the disk emits as light. The exact mechanism that produces jets is still debated, but it seems to involve the interaction between the black hole's spin, the accretion disk, and strong magnetic fields. One leading model is the Blandford's-Narjek process. In this mechanism, magnetic field lines threading through the black hole's horizon extract rotational energy from the black hole itself, channeling it into the jets. Another model involves the disk's magnetic fields, which can become twisted and amplified by the disk's rotation, forming a kind of magnetic tower that accelerates particles outward along the rotation axis. Both processes may contribute, and the relative importance of each might depend on the black hole's spin and the properties of the accretion flow. Relativistic jets are observed around many supermassive black holes and some stellar mass black holes. In supermassive black holes, the jets can extend for millions of light years, far beyond the host galaxy, creating enormous lobes of radio-emitting plasma. These radio galaxies are among the largest structures in the universe, dwarfing even the largest galaxy clusters. The jets interact with the intergalactic medium, creating shock waves, heating gas, and influencing the evolution of galaxy clusters. They can suppress star formation by heating the gas that would otherwise cool and collapse to form stars, providing a form of feedback that regulates the growth of the most massive galaxies. In stellar mass black holes, jets are observed in systems called microquasars, where a black hole is accreting matter from a companion star. The jets in microquasars are much smaller than those in supermassive black holes, extending only light years or tens of light years, but they exhibit similar physics and provide a nearby laboratory for studying jet formation. One famous microquasar is Cygnus X1, the first stellar mass black hole to be discovered. It's a binary system where a black hole of about 15 solar masses orbits a massive blue supergiant star. Gas from the star flows toward the black hole, forming an accretion disk that emits intense X-rays. Occasionally, the system launches jets, visible in radio wavelengths. Accretion disks also exhibit variability. The brightness of the disk can change on timescales from milliseconds to years, depending on the mass of the black hole and the details of the accretion flow. This variability provides clues about the dynamics of the disk and the environment near the black hole. In some cases, the disk becomes unstable, leading to dramatic outbursts. In X-ray binaries, these are called X-ray transients. The black hole remains relatively dim for years or decades, then suddenly brightens by factors of thousands or millions as a large amount of matter falls in. These outbursts can last for months before the system returns to quiescence. The spectrum of light from an accretion disk also carries information about the black hole's properties. The thermal emission from the disk peaks at a wavelength that depends on the temperature of the innermost regions, which in turn depends on the black hole's mass and spin. Iron atoms in the disk emit characteristic X-ray lines, and these lines are broadened and shifted by the extreme gravity near the black hole, creating a distinctive profile that can be used to measure the black hole's spin and the geometry of the disk. Accretion is not perfectly efficient. Most of the gravitational potential energy of the infalling matter is converted to radiation and carried away, but some is carried into the black hole. The efficiency depends on the black hole's spin. For a non-rotating black hole, about 6% of the rest mass energy of the infalling matter is converted to radiation. For a maximally spinning black hole, the efficiency can be as high as 42%. This is far more efficient than nuclear fusion, which converts less than 1% of rest mass into energy. This efficiency makes accreting black holes some of the brightest objects in the universe. A quasar powered by a supermassive black hole can shine with the light of trillions of suns, all from a region just light hours across. This is why quasars can be seen from billions of light years away, their light carrying information about the conditions in the young universe. Accretion is also how black holes grow. Every particle that crosses the event horizon adds its mass to the black hole. Over millions of years, a black hole can double or triple its mass through accretion, growing from a stellar remnant to an intermediate mass black hole, or from an intermediate mass black hole to a supermassive one. But accretion is self-limiting. As more matter falls in, the disk becomes brighter, and the radiation exerts an outward pressure that can push away additional material. This is the Eddington limit, the maximum luminosity a black hole can sustain through accretion, without blowing away its fuel. For a given mass, there's a maximum rate at which a black hole can grow through steady accretion. To grow faster, black holes need short bursts of rapid infall, or they need to merge with other black holes. Mergers add mass instantly, bypassing the Eddington limit, and they're likely an important mechanism for the growth of supermassive black holes, especially in the early universe. Accretion disks and jets are the interface between black holes and the rest of the universe. They are where the invisible becomes visible, where the silent becomes loud, and where the influence of black holes extends far beyond their event horizons, shaping galaxies, clusters, and the cosmos itself. Strange phenomena and mysteries. Black holes are strange enough on their own, but the universe has found ways to make them even stranger. Beyond the basics of event horizons and singularities lie phenomena that challenge our understanding, speculative ideas that push the boundaries of physics, and mysteries that remain unsolved despite decades of effort. One such phenomenon is the photon sphere, a spherical region around a black hole where gravity is so strong that light can orbit in circles. For a non-rotating black hole, the photon sphere lies at 1.5 times the Schwarzschild radius, or 1.5 times the radius of the event horizon. At this distance, photons traveling tangentially to the sphere can orbit the black hole indefinitely, tracing out circular paths. These orbits are unstable. Any slight perturbation, and the photon either falls into the black hole or escapes to infinity. But in theory, if you stood at the photon sphere and looked around, you would see strange, distorted images of the universe, with light from distant stars bent and magnified by the black hole's gravity. You might even see the back of your own head, as light from you orbits the black hole and returns to your eyes from behind. For a spinning black hole, the situation is even more complex. The photon sphere becomes a photon region, a zone where different circular orbits exist at different radii, some prograde, moving in the direction of the black hole's spin, and others retrograde, moving against it. The structure of this region depends on the black hole's spin, and it affects the appearance of the shadows seen by distant observers. Around a spinning black hole lies another strange region called the ergosphere. This is a volume of space outside the event horizon where space-time is dragged around so strongly by the black hole's rotation that nothing can remain stationary. Even light would be pulled around in the direction of the spin. But within the ergosphere, escape is still possible. You can still move outward, away from the black hole if you're willing to move with the rotation. The ergosphere exists because of frame dragging, the way a spinning mass twists space-time around it. This effect has been measured near Earth using satellites. The Gravity Probe B mission, for example, detected the tiny amount of frame dragging caused by Earth's rotation, confirming yet another prediction of general relativity. Near a black hole, frame dragging becomes extreme, creating the ergosphere and enabling processes like the Penrose mechanism for extracting energy from the black hole's spin. In theory, the laws of physics allow for even stranger objects. A naked singularity, for example, would be a singularity without an event horizon, exposed to the outside universe. Such an object is prohibited by the cosmic censorship conjecture, a hypothesis proposed by Roger Penrose which states that singularities must always be hidden inside event horizons. But the conjecture has never been proven, and some solutions to Einstein's equations do allow for naked singularities under special conditions. If a naked singularity existed, it would be a place where the laws of physics, as we understand them, break down in view of the rest of the universe. It's unclear what would happen, but it would likely involve violations of causality, unpredictability, and other features that make physicists uncomfortable. Most researchers believe that cosmic censorship holds, and that naked singularities do not exist in nature, but the question remains open. Wormholes are another theoretical possibility. These are tunnels through space-time, connecting two distant regions of the universe or even two different universes. Solutions to Einstein's equations that describe wormholes exist, but they require exotic forms of matter with negative energy density, something that has never been observed and may not exist. Even if wormholes could be created, they would likely be unstable, collapsing too quickly for anything to pass through. And even if they could be stabilized, traversing one would be extraordinarily dangerous. Tidal forces, radiation, and quantum effects near the wormhole's throat might destroy anything that tried to pass through. Despite these challenges, wormholes remain a staple of theoretical physics and science fiction, symbolizing humanity's desire to transcend the limitations of distance and time. Some researchers have explored the idea of using wormholes for time travel, another speculative concept allowed by the equations of general relativity under certain conditions. But time travel comes with its own paradoxes. Like the famous grandfather paradox, and most physicists believe that the universe somehow prevents such paradoxes from occurring, perhaps through quantum effects or hidden consistency constraints. Black holes themselves raise deep questions about the nature of information and reality. The black hole information paradox, which we discussed earlier, remains one of the most important unsolved problems in theoretical physics. If information is truly lost when a black hole evaporates, it would violate the principles of quantum mechanics, which require that information be preserved. But if information is not lost, where does it go? How does it escape from behind the event horizon? Recent theoretical work suggests that the paradox may be resolved by recognizing that the interior and exterior of a black hole are not as independent as they seem. Quantum entanglement between particles inside and outside the horizon might allow information to leak out gradually in subtle correlations in the Hawking radiation. This would require a profound revision of how we think about space-time and black holes, but it would preserve the fundamental principles of quantum mechanics. Another mystery involves the singularity itself. At the heart of every black hole, the mathematics of general relativity predicts a point of infinite density and infinite curvature. But infinity is a sign that the theory has broken down, that it's being pushed beyond its limits. Most physicists believe that a complete theory of quantum gravity, a theory that unifies general relativity and quantum mechanics, would eliminate the singularity, replacing it with something more exotic but still describable by physics. What that something is remains unknown. String theory, loop quantum gravity, and other approaches to quantum gravity offer different possibilities, but none has been tested observationally. The interior of a black hole remains one of the great unknowns, a place where our equations fail and new physics must take over. There's also the question of what happens to black holes in the far future. If the universe continues to expand forever, as current observations suggest, then eventually all matter will either decay or be pulled into black holes. The black holes will then slowly evaporate through Hawking radiation. In the final moments of a black hole's life, when it's very small and very hot, quantum effects should become important. What happens then? Does the black hole explode? Does it leave behind a remnant? Does information re-emerge in some form? We don't know. The final stages of black hole evaporation probe regimes of physics that we cannot yet describe. They may involve phenomena beyond general relativity and quantum field theory, requiring a fully developed theory of quantum gravity. Black holes also raise philosophical questions. They are the ultimate limits of observation. Nothing that happens inside an event horizon can ever be observed from outside. This means there are parts of the universe that are, in principle, forever beyond our reach. We can calculate, predict, and theorize, but we can never directly observe the interior of a black hole and return to tell the tale. This limitation is both humbling and exciting. It reminds us that there are boundaries to knowledge, places where the universe keeps its secrets. But it also drives us to be creative, to find indirect ways of probing the unknown, to push the limits of theory and observation, and to never stop asking questions. Black holes are not just objects, they are laboratories, testing grounds for our most fundamental theories. They are puzzles, challenging us to reconcile gravity with quantum mechanics. And they are mysteries, reminding us that the universe is stranger and more beautiful than we ever imagined. The history of black hole discovery. The story of black holes begins not with telescopes, but with mathematics. In 1796, over a century before Einstein, the French mathematician Pierre-Simon Laplace speculated about what he called dark stars. He reasoned that if a star were massive enough and compact enough, its escape velocity could exceed the speed of light. Light itself could not escape such an object, rendering it invisible. Laplace's speculation was based on Newtonian physics, which treated light as particles. When the wave nature of light was later established, his idea fell out of favor. It wasn't until the early 20th century, with Einstein's general theory of relativity, that the concept of black holes would be revived on firmer theoretical ground. Just months after Einstein published his field equations in November 1915, Karl Schwarzschild, a German physicist serving in the German army during World War I, found an exact solution. Despite being stationed on the Russian front and battling a painful autoimmune disease that would soon claim his life, Schwarzschild worked through Einstein's equations and discovered something remarkable. His solution described the space-time geometry around a perfectly spherical, non-rotating mass. It predicted that if enough mass were compressed into a small enough volume, a boundary would form beyond which nothing could escape. This boundary is what we now call the event horizon, and its radius, the Schwarzschild radius, is the defining feature of a black hole. Einstein himself was troubled by Schwarzschild's solution. He believed it represented a mathematical curiosity rather than a physical reality. The idea that something could become so dense that it disappeared behind an event horizon seemed too strange, too extreme. For decades, many physicists agreed. Black holes were mathematical possibilities, but surely nature would not permit such extremes. The debate continued through the middle of the 20th century. In 1939, J. Robert Oppenheimer and Hartland Snyder published a paper showing that a sufficiently massive star, once it exhausted its nuclear fuel, would collapse under its own gravity without limit, forming what we now recognize as a black hole. But even this work was largely ignored, overshadowed by the outbreak of World War II and the subsequent development of nuclear weapons, in which Oppenheimer would play a leading role. It wasn't until the 1960s that black holes began to be taken seriously as physical objects. Several developments contributed to this shift. Astronomers discovered quasars, incredibly luminous objects billions of light years away, that seemed to be powered by something far more efficient than nuclear fusion. The only plausible explanation was matter falling into supermassive black holes, converting gravitational potential energy into light with remarkable efficiency. At the same time, X-ray astronomy was born. Detectors flown on rockets and satellites revealed sources of X-rays that couldn't be explained by ordinary stars. Some of these sources appeared to be compact objects, perhaps neutron stars or black holes, accreting matter from companion stars and emitting X-rays from the superheated material. The term black hole itself wasn't coined until 1967, when physicist John Wheeler used it in a lecture. Before that, they were called frozen stars because of the time dilation effect that makes their collapse appear to freeze from the perspective of a distant observer. Wheeler's catchy name stuck, and it helped popularize the concept among both scientists and the public. The first strong candidate for a black hole was Cygnus X1, discovered in 1964 as an X-ray source and identified in 1971 as likely containing a black hole. The system consists of a visible blue supergiant star and an invisible companion. By studying the star's motion, astronomers determined that the unseen companion had a mass of about 15 times that of the Sun, far too massive to be a neutron star. The only known object that could have such a mass without emitting light was a black hole. For years, the existence of black holes remained controversial. Some scientists argued that the evidence was circumstantial, that alternative explanations might exist. But as more candidates were discovered and studied, the case grew stronger. By the 1990s, the existence of stellar mass black holes was widely accepted, and evidence for supermassive black holes at the centers of galaxies was mounting. The discovery of gravitational waves in 2015 provided the most direct evidence yet. The first detected signal, GW1F20T, came from the merger of two black holes more than 1 billion light-years away. The signal matched theoretical predictions with extraordinary precision, confirming not only the existence of black holes but also their ability to merge and the reality of gravitational waves themselves. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the dark region created by the Event Horizon's capture of light. This image of the supermassive black hole in galaxy MAT7 provided visual confirmation of black holes' existence and verified predictions about their appearance. 3 years later, they released an image of Sagittarius A star, our own galaxy's central black hole. From mathematical curiosities to directly observed objects, black holes have completed a remarkable journey through the history of science. What began as speculative ideas from Laplace and exact solutions from Schwarzschild has become one of the most thoroughly studied and confirmed predictions of general relativity. Today, black holes are not just accepted, but are recognized as fundamental components of cosmic structure, essential to understanding galaxy evolution, gravitational wave astronomy, and the ultimate fate of massive stars. The search continues, however. Intermediate mass black holes remain elusive, with only a handful of candidates identified. Primordial black holes, if they exist, have yet to be detected. And the interior of black holes remains forever hidden, a realm where our theories break down and new physics must emerge. But the progress has been extraordinary. In little more than a century, black holes have gone from theoretical impossibilities to observed realities, from objects that troubled Einstein to tools for exploring the universe. They are monuments to human curiosity, to the power of mathematics, and to the strange beauty of nature itself. Black holes in the universe. Black holes are not rare cosmic curiosities. They are woven into the fabric of the universe, scattered throughout galaxies, shaping the evolution of stars and galaxies and playing crucial roles in the history of the cosmos. Our Milky Way galaxy is home to an estimated 100 million stellar mass black holes. Most of these are solitary, drifting through space unseen, the remnants of massive stars that died billions of years ago. They are invisible, emitting no light, interacting with nothing unless something happens to pass close enough to be captured by their gravity. Occasionally, a black hole finds a companion. If a black hole forms in a binary star system, where two stars orbit each other, it can remain bound to its companion even after the supernova. The surviving star, if it's massive and evolves into a giant, can begin to shed material onto the black hole, forming an accretion disk that glows with X-rays. These are X-ray binaries, and they're among the brightest X-ray sources in the galaxy. Cygnus X1, discovered in the early 1970s, was the first stellar mass black hole to be identified. It's a binary system where a black hole of about 15 solar masses orbits a blue supergiant star. The black hole pulls gas from the star, heating it to millions of degrees and producing intense X-ray emission. For decades, Cygnus X1 was one of the strongest pieces of evidence that black holes exist, and it remains one of the most studied black hole systems in the sky. Not all black holes in binaries have stellar companions. Some orbit other black holes. These binary black holes are the sources of the gravitational waves detected by LIGO and Virgo. They're thought to form through several mechanisms. In some cases, two massive stars in a binary system both collapse to black holes, remaining bound to each other. In other cases, black holes find each other in dense stellar environments like globular clusters, where chance encounters can lead to captures and binary formation. Once a binary black hole forms, it slowly loses energy and angular momentum through gravitational waves. The orbit shrinks, the black holes draw closer, and the rate of energy loss accelerates. Eventually, they spiral together and merge in a final burst of gravitational radiation, creating a single, more massive black hole. The rate at which these mergers occur is higher than astronomers expected before LIGO began operations. Tens or even hundreds of binary black hole mergers are detectable every year by current instruments, suggesting that the universe has been quite efficient at producing black holes and pairing them up. Rogue black holes, those unbound to any star or companion, wander through the galaxy like cosmic nomads. They're nearly impossible to detect unless they happen to pass in front of a distant star, creating a gravitational lensing event that briefly brightens the star. Surveys searching for such events have found a handful of candidates, hinting at a large population of solitary black holes drifting unseen through space. Some black holes might even pass through our solar system, though the chances of this happening are incredibly small. If a stellar mass black hole did pass through, it would exert gravitational perturbations on the planets, altering their orbit slightly, but it wouldn't pose a direct threat unless it passed extraordinarily close, which is astronomically unlikely. At the centers of galaxies, supermassive black holes dominate. They are not wandering but anchored, sitting at the gravitational heart of their host galaxy, surrounded by dense clusters of stars and gas. Their influence extends over thousands of light years, affecting the orbits of stars and the flow of gas throughout the galactic center. When galaxies merge, their central black holes eventually sink to the center of the new, combined galaxy. This process takes millions of years. The black holes interact with stars, scattering them and losing energy, which causes the black hole's orbit to shrink. Eventually, the black holes get close enough that gravitational wave emission becomes important, and they spiral together in a final plunge. This process is called a major merger if the galaxies are of similar size, or a minor merger if one galaxy is much smaller. The Milky Way has experienced many minor mergers over its history, absorbing smaller dwarf galaxies and stripping them of their stars. Each of these dwarf galaxies likely had its own central black hole, and those black holes should still be somewhere in the Milky Way's halo, slowly sinking toward the center. Intermediate mass black holes, those in the 100 to 100,000 solar mass range, are harder to find. They don't live at the centers of large galaxies, and they don't form from single stellar collapses. Instead, they might reside in dense star clusters, globular clusters, or dwarf galaxies. Some globular clusters show evidence for central black holes. Stars near the center of these clusters move faster than expected, as if pulled by an unseen mass. The inferred masses are in the hundreds to thousands of solar masses consistent with intermediate mass black holes. But the evidence is not always conclusive, and some researchers argue that the motions could be explained by a dense cluster of stellar remnants rather than a single black hole. Dwarf galaxies, small galaxies with only millions to billions of stars compared to the hundreds of billions in the Milky Way, sometimes harbor intermediate mass black holes at their centers. These galaxies are thought to be the building blocks of larger galaxies, merging over time to form the massive galaxies we see today. If so, their central black holes would merge as well, contributing to the growth of supermassive black holes. The population of black holes in the universe evolves over time. In the early universe, when stars were forming rapidly and many were massive and short-lived, black holes formed frequently. As the universe aged and the star formation rate declined, fewer new black holes were born. But existing black holes continued to grow through accretion and mergers. Supermassive black holes were actively feeding in the early universe, powered by the abundant gas and frequent mergers of that era. This was the age of quasars, when supermassive black holes blazed with the light of trillions of suns. Today, most supermassive black holes are quiescent, having exhausted their fuel or expelled it through feedback processes. In the far future, black holes will be among the last survivors. Long after the stars have burned out, black holes will remain, slowly accreting the occasional wandering object and emitting faint Hawking radiation. Eventually, even the black holes will evaporate, leaving behind only radiation and, perhaps, remnants too small to observe. The universe will then enter its final era, a cold, dark expanse where nothing happens, where all structure has decayed, and where entropy has reached its maximum. This is sometimes called the heat death, the ultimate fate of a universe governed by the laws of thermodynamics. But that is trillions upon trillions of years in the future. For now, black holes are active participants in the cosmic drama, growing, merging, feeding, and shaping the galaxies they inhabit. They are not endpoints, but chapters in an ongoing story, a story written in gravity and light, in space-time and quantum foam, in the collisions of giants and the faint whispers of evaporation. The universe is full of black holes. They are everywhere, hidden and powerful, waiting to be discovered, studied, and understood. And with each new detection, each new observation, each new theory, we come a little closer to unraveling their mysteries. Closing thoughts. We've journeyed tonight through some of the most mysterious, most powerful, and most misunderstood objects in the universe. Black holes, regions of space-time where gravity has become so intense that not even light can escape, where time itself behaves strangely, and where the laws of physics reach their limits. We've talked about how they form, from the deaths of massive stars to the assembly of supermassive giants over billions of years. We've explored their properties, the event horizons that mark the point of no return, the singularities hidden at their cores, the strange phenomena like time dilation and frame dragging that arise from the warping of space-time. We've discussed Hawking radiation, the quantum process that allows black holes to slowly evaporate, proving that even the most seemingly eternal objects have finite lifespans. We've listened to the gravitational waves from merging black holes, ripples in space-time that carry information from some of the most violent events in the cosmos. We've glimpsed the supermassive black holes at the centers of galaxies, seen their images captured by the Event Horizon Telescope, and learned how they shaped the evolution of their hosts. We've explored accretion disks and jets, the interface where black holes interact with the rest of the universe. And we've touched on the mysteries and paradoxes that still challenge our understanding. We've traced the history of their discovery, from Laplace's speculation to Schwarzschild's solution, from the skepticism that greeted them to the observational confirmation that established them as real. We've seen how they went from mathematical impossibilities to observed phenomena, from objects that troubled Einstein to cornerstones of modern astrophysics. And we've been reminded that black holes are not rare, not exotic anomalies, but integral parts of the universe, scattered throughout galaxies, playing crucial roles in the cosmic story. Black holes teach us profound lessons about the nature of reality. They show us that space and time are not the rigid stage on which events unfold, but flexible, dynamic entities that bend and curve in response to mass and energy. They demonstrate that what seems impossible by everyday intuition, light being trapped, time slowing to a halt, space folding back on itself, can be not only possible but inevitable under the right conditions. They challenge our understanding of information and determinism. If information can be destroyed in a black hole, then the future is not determined by the past, and the fundamental principles of quantum mechanics must be revised. But if information is preserved, then black holes must be far more complex than they appear, with hidden structures and connections we are only beginning to glimpse. They remind us of the limits of knowledge. The interior of a black hole is forever hidden from external observers. We can theorize, calculate, and predict, but we can never directly observe what happens inside the event horizon and return to share that knowledge. There are boundaries to what we can know, places where the universe keeps its secrets. Yet within these limits, we have learned so much. We have mapped the properties of black holes across the cosmos. We have measured their masses and spins. We have watched them merge and detected the gravitational waves they produce. We have imaged their shadows and studied their accretion disks. We have traced their influence on galaxies and their role in cosmic evolution. Each discovery reveals new questions. How do supermassive black holes form so quickly in the early universe? What happens to information that falls into a black hole? Are there intermediate mass black holes hiding in dense star clusters? Do primordial black holes exist, and could they account for dark matter? What replaces the singularity when quantum effects are included? These questions drive research forward. They inspire new telescopes, new detectors, new theoretical frameworks. They bring together astronomers, physicists, mathematicians, and computer scientists in collaborative efforts, spanning continents and decades. They represent the frontier of human knowledge, the edge where the known meets the unknown. But beyond the science, beyond the equations and observations, black holes speak to something deeper. They remind us of our place in the cosmos. We live on a small planet orbiting an ordinary star in an average galaxy containing hundreds of billions of stars. And that galaxy, in turn, is one of hundreds of billions of galaxies in the observable universe. The scales are so vast as to be almost incomprehensible. Yet within this vastness, complexity emerges. Stars form, live and die. Planets coalesce from the debris, and on at least one planet, perhaps many others, matter organizes itself into living systems capable of contemplating their own existence and the universe that contains them. We are, in a very real sense, the universe becoming aware of itself. We are made of atoms forged in the cores of stars and scattered by supernovae, the same events that create black holes. We are connected to these distant, powerful objects not just through gravity, but through shared history, through the cosmic processes that shape both black holes and living beings. In studying black holes, we study our origins. We trace the pathways by which matter and energy flow through the universe, creating structure, complexity, and ultimately life. We see the grand cycles of birth and death that operate on scales from individual stars to entire galaxies. We glimpse the distant future when black holes will be among the last survivors, slowly evaporating in a cold, dark cosmos. This perspective can be humbling. Our individual lives, our worries and stresses can seem small and fleeting against the backdrop of cosmic time, but it can also be liberating, knowing that we are part of something so vast, so ancient, so filled with mystery and beauty, can bring a sense of peace and wonder. Tonight, as you drift towards sleep, let these thoughts settle gently in your mind. You are made of stardust, connected to the cosmos through billions of years of history. The same forces that create black holes also created you. The same laws that govern the motion of galaxies also govern the atoms in your body. You are small, yes, but also precious, rare. A momentary flowering of complexity in a universe trending towards simplicity. A consciousness capable of wonder, of curiosity, of love and fear and hope. For a brief time, the universe has organized itself in such a way that it can look back at itself through your eyes and marvel at its own existence. Rest in that knowledge. Let it carry you gently into sleep, knowing that whatever challenges tomorrow brings, you are part of something larger, something beautiful, something worth exploring and understanding. And remember, the universe is still revealing itself. New discoveries await, new mysteries will emerge. The story of black holes, like the story of the cosmos itself, is far from over. There are always more questions to ask, more observations to make, more theories to test. But for now, rest. Let curiosity and calm coexist. Let wonder and peace embrace. The black holes will still be there tomorrow, patient and powerful, waiting to be studied, waiting to reveal more of their secrets. If you've enjoyed this exploration, if it's helped you relax and drift towards sleep, please consider liking this video and subscribing to the Sleepy Scientist's channel. Your support helps me create more content like this, more journeys through the cosmos, more stories from the universe, one sleepy soul at a time. Thank you for joining me tonight. Thank you for your curiosity, your openness, your willingness to explore these strange and beautiful corners of reality. May your dreams be filled with stars and wonder, and may you wake tomorrow with a sense of connection to the vast, ancient, mysterious universe that is your home. Rest well, sleep deeply, and know that out there, across billions of light years, black holes are dancing, stars are being born, and the universe continues its grand journey through time. Good night.